I hope you're all doing well today this morning. I am Mr. Ish. Thank you for joining me. In this video, we're looking very quickly and easily at what a complex number is. You can represent it in this form, x plus yi. Some of you will be familiar with a plus bi. Complex number is x plus yi, but the complex number designation is z. Why is it called a complex number? Because it is made of a real number component and an imaginary number component right here. You can do everything here with regards to a complex plane. A complex plane has an x-axis and it has a y-axis. The real axis or the imaginary axis, you can always plot a point x comma y such that that point will represent your complex number. When you're looking here, you're isolating that, you're looking at x comma y. That x comma y will represent a complex number in terms of its designation or location on a complex plane. How do you understand what the components of a complex number are? In addition to it having a real and imaginary, well then you must look at two items, the modulus of a complex number and the argument of a complex number, because these two items are needed to plot your complex number on a complex plane. The modulus is equivalent to basically like a radius. I'm not saying it is, I'm saying it's equivalent to like a radius. The argument is equivalent to like a theta. That's how you'd want to think about it. And you know, radius, if you're thinking about a unit circle, is always coming from a right triangle trigonometry. A square plus b square is equal to c square, or in this particular case, your c representing your radius, it would be equal to square root of a square plus b square. You can always think of it in that way. But when you're looking at it in terms of a complex number, you can think of your modulus by means of this very easy formula. Your modulus, which we'll symbolize as an r, is equal to the square root of your x component squared and the y component squared, and that sum of that. The argument determination is no different than you doing the determination for the direction of a vector. Here you're going to do your inverse tan, which would be represented by y over x. Your imaginary number component or by real number component, and this right here will give you the angle that's involved in terms of how you can plot it out. You can see you have a specific dimension here, or you have a specific dimension here, the angle, all of which come into play with a complex number. If I tell you I have a complex number which looks like this, which is 2 minus 3i, and I want to determine the components of this complex number, how can I do it? And then represent the answer in a good form, I will show you. You are first converting this into 2 comma minus 3, and then you're looking at that in terms of a complex plane. You know you're looking here at 2 and you're looking here at a minus 3. That's 2 comma minus 3. You have to determine the modulus. The modulus is equal to the square root of the individual components squared. You're looking here at 2 squared plus minus 3 squared, and that's not hard. 4 plus 9 root 13. What about my argument? What's the argument over here? Argument is exactly right there. The inverse tan. The inverse tan of your y component minus 3 divided by your x component, always being adjusted for a reference horizontal, either 0 degrees or 360 and or 180 right over here. You would need to bring the calculator. You'll do 3 negative divided by 2 inverse tan. I know it's falling here in the fourth quadrant. I'll adjust it with 360. I'll add 360 and I'm getting 303.7 degrees. You can keep this here in degrees if you want, 303.7 degrees. But what do I do with this now? You convert the complex number in this general form into a polar form, or you can say the trigonometric form. That's what you do. And how do you do that? You look at their designation. It's always this, r cosine theta plus I sine theta. That right there is a representation of a complex number in a polar or trigonometric form. This right here is representation of a complex number in a general form, or you can say x plus yi. And of course you can always bring in the minuses. Let's convert this outcome into a polar trigonometric form. I have root 13, which is my r. Then I do cosine 303.7 plus I sine 303.7. Why am I putting a plus here and not a minus? Because I know the sign of 303 is a negative. It would automatically convert this into a minus if you were to open this up. If you were to open this up, multiply this with the outcome of that and this with the outcome of that, you should end up with 2 comma minus 3, and you will. And I will show you. You'll do root 13 multiplied by that saved angle 303 cosine of it, and I'm getting 2. Now I'll do root 13 and I'll multiply it by the saved angle but the sign of it, and it'll bring in a negative value. I'll get -3. That's exactly how you can check it. Here is your general form of a complex number. Z is equal to each of these, and here is your polar or trigonometric form of a complex number. And now you're seeing how you're doing it. There's a modulus, which is kind of representing the distance like a radius, and here's the argument, which is representing the direction of that complex number. Let's look at one more example and then we can wrap it up. We have a complex number that's represented as z is equal to -2 plus I. We have to convert this into a polar trigonometric form, for which you need to determine the modulus and the argument, but we'll graph it first on a complex plane. -2 and 1, because you're looking here at a -2 comma 1. The I is synonymous with 1. -2 comma 1, that's what I have, and I'm looking at that. I have to determine the modulus. You know, you're looking at the square root of the individual component squared. -2 squared plus 1 squared. What do I have? √5. Now I'm looking at the argument. The argument is easy. You're looking here at the inverse tan of the y component, which is 1, divided by the x component, which is -2. Y over x. Always y over x. Your sine divided by your cosine. 1 divided by 2 minus, I'm going to do inverse tan. I'm getting that, but I'm going to adjust it by means of the reference horizontal 180. I'll add it to 180. I get 153.4 degrees. You want to convert this into radians, you can. I'm keeping this in degrees. If you want to convert this to radians, you multiply it by pi over 180. But we don't need to do that because we're keeping things straight and to the point. Now let's convert this complex number general form into the polar or trigonometric form. You have a √5, which is your r, and then you're multiplying by your argument, which we'll put here in the proper form. Cosine 153.4 plus I sine 153.4. We will end by checking this answer. I've saved the angle in my calculator. We'll do √5 multiplied by that angle cosine, and I'm gonna get -2, which is what I wanted. I'll do that same angle, sine it, and multiply it by √5, which is my modulus, and I'm getting a 1, which is what I wanted. So now you're seeing everything is good. Remember, a complex number has a real component, which is this part right here, and an imaginary number, which is this part. That's why it's called complex, because it has representatives of imaginary and real numbers. Thank you for watching. Have a good day.